Okay, today we talked about pressure and temperature and what gases are to try to get our feet wet a little bit. And tonight's homework is actually talking to you a little bit about how to convert with pressure and temperature and what to do with that. So that should be a pretty simple task if you've already done that, and you should be working on that. Tonight, I want you looking at some notes about the guys who studied gases. We're talking about Robert Boyle, Jacques Charles, Joseph Gay-Lussac. Also, some people call this no name because there were several people who were looking at that particular one, and he was just given credit for it for some reason. Not sure if that's appropriate. And then finally, Avogadro's law. Those are the four that we're going to be talking about a little bit. So Boyles Law. Boyles Law says pressure is inversely proportional. That's a pretty important term in terms of some of the things that we know. Inversely proportional to volume when temperature is held constant. So T is constant. We know that we're not going to change temperature. And you're going to find that's going to be an important part of all of these laws. So that means inverse means as pressure goes down, volume goes up. Now we're going to see some demonstrations tomorrow and some videos of demonstrations tomorrow that are going to help us better understand that and see it actually in action. So don't panic. I'm just not showing those videos right now because it's going to take too much of the time. So P1 V1 is equal to P2 V2. So you need to know three of these items to solve for one of them. And it doesn't matter. As long as temperature is being held constant, Boyle's law should be coming into play. Notice that we have a graph here, volume and pressure, and notice that it's a curve. This is when we know it's an inverse proportion, when we graph the two against each other and we get this giant curve. Now we could make it a straight line by graphing 1 over volume versus P, and that gives us a straight line. Okay? So that's something important that we need to look at as well, because we can make straight line relationships with things based upon how we reconfigure them. The next guy is Charles' law. Charles' law says that the volume of gas is directly, notice a different word, directly proportional to temperature and extrapolates to 0 at 0 Kelvin. So 0 Kelvin is pretty important. That word right there is really important. Notice P is constant. So volume going up means that the temperature should go up. Volume going down means the temperature should go down, and vice versa. That's what a direct proportion is. They move in the same direction. Inverse means they move in opposite directions. So we see a little bit of a different version here. Notice P is held constant, so P is nowhere in the equation. We see that V1 over T1 is equal to V2 over T2. When pressure is held constant, you know that Charles' law is in play there. So we see that if we have three of these, any three of them, we can solve for the other. This is the graph. Notice the direct proportionality. Because they're directly proportional, we see a straight line relationship versus the indirect proportional or the inverse proportion when we saw the curve. That's pretty important because we can tell graphically if something is directly proportional or indirectly proportional just by looking at the graph as well. Next guy is Gay-Lussac's, or, oh, I'm sorry, let me go back. Temperature must be in Kelvin. Why? Well, if we use negative degrees Celsius, we're going to get a negative volume. And since a negative volume is not possible, we can't use anything but Kelvin. So in gas law work, you're always changing your temperature to Kelvin. Okay? No names or Gay-Lussac's law. Now, some people call it no names law because there were several men working on the stuff at the same time, so they didn't want to give just one guy any particular credit. So we see that we have Gay-Lussac's law. It says that pressure and temperature of a gas are directly related. So here we go. Here's another time that we see this idea of a direct relationship, provided that volume remains constant. So V is constant. So that means if pressure goes up, so does temperature. If pressure goes down, so does temperature, and vice versa. So again, you're going to expect something here. So what should this equation look like? Well, the direct equation for the last one had the two divided by each other. The indirect equation, or inverse proportional equation, had them multiplied by each other. So you're right if you said that they should be divided by each other. P1 divided by T1 is equal to P2 divided by T2. And so that's the indirect relationship. Also, what should the graph look like according to what we just saw? Inverse is a curve. The direct relationship was a straight line. So should this be a curve or a straight line? You're absolutely right. It should be a straight line. And there it is. Notice this extrapolation here. We may have measured at P here, but we can extrapolate down to 0K because we always need temperature in Kelvin. Once again, temperature must be in Kelvin. So just like in the last one, there's an extrapolation point that we can get to 0 Kelvin. That should be 0 pressure. All right, last one. Oh, no, I'm sorry, combined gas law. So we're going to combine all of them. So that means nothing is held constant. So if you have a problem that has all three and nothing is held constant, you may be looking at the combined gas law. So we're looking at the relationship between all three of them with a fixed amount of gas. So the thing that is not changing is the amount of gas. So the amount of gas is the same. What's going to happen? Well, there's the relationship. Notice the top part of it is Boyles Law. The bottom part of it is what we got from both Charles and Gay-Lussac's. Notice this is Charles' law right here, and this one is Gay-Lussac's law. So we're just combining everything and putting it together. In this particular case, you would need to know 5 of the 6 in order to solve one. Any 5 of the 6 you need to know to be able to solve the other one. And that's how you know. If things are not being held constant, but you're given several different things, that's when we're going to use combined gas law. Now finally, this law is a little bit different, and it's kind of got the same idea, but it has to do with Avogadro's number. And we know when we hear Avogadro's number, that is going to be talking about moles. So Avogadro's law for the gas at constant temperature and pressure. So now we have 2 constants. Temperature and pressure are going to be kept constant. The volume is directly proportional to the number of moles of gas. Now, it's saying at low pressure, so we're going to keep the pressure relatively low to do this. Now, we already know this because we know that 1 mole of any gas at STP, and STP means 1 atmosphere, and 273 Kelvin has a volume of 22.4 liters. So that's a relationship that we already know. So this is just saying, okay, what happens if the temperature and pressure aren't at STP? What happens if the temperature and pressure are at, 2 atmospheres and 200 Kelvin? What's happening there with volume and number of moles, and can we figure that out? And the answer is yes, because we see another direct proportionality. That means we're going to have an equation that is being divided. So we see that we have N1 over V1 is equal to N2 over V2. Once again, we have this direct relationship that gives us this division quotient instead of giving us a indirect relationship and it being multiplied by each other. So when we see this, we know that temperature and pressure are going to be constant. They will give us temperature and pressures unless they tell us STP. But if we're not given STP, then we have to assume that some things are going to change, and we can calculate one of the 4 if we know the other 3, just like we could in all the others. Now tomorrow we're going to be doing some demonstrations for you to see this and some problems and trying to get used to that. So thank you very much for listening, and I will talk to you later.